All of the reactions that we looked at so far go in one direction, the forward direction in which the reactants form products. There are many reactions in which the products reform the reactants. Those are called reversible reactions or equilibrium reactions. We will look at equilibrium reactions in this video. Let's take a look at an equilibrium reaction. Reactants A and B react to form products C and D. Products C and D react to reform reactants A and B. At some point, the concentrations of reactants and products will be constant. This condition is called equilibrium. We can quantify the relative amounts of reactants and products with an equilibrium constant. Equilibrium constant is the ratio of the product of concentration of products to the product of concentration of reactants. Here's an example. Reactants A and B are in equilibrium with products C and D. Here is our equilibrium constant expression. Each concentration is raised to the power of the coefficient in the balanced chemical equation. What does equilibrium constant mean? Stop the video and answer these two questions. And the answers are... Let's take a look at these graphs of concentration of reactants and products with time, that is, as the reaction proceeds. When the concentrations of reactants and products no longer change, that is, they're constant, the reaction is at equilibrium. Stop the video and determine which graph has an equilibrium constant greater than 1. And the answer is... Acetic acid is the acid in vinegar. It reacts with water in an acid-base reaction. The equilibrium constant for this reaction is 1.8 times 10 to the minus 5. Stop the video and answer these questions. And the answers are... Since the equilibrium constant is less than 1, this tells us acetic acid partially dissociates into its ions, which makes acetic acid a weak acid. What does an acetic acid solution look like? Stop the video and answer these questions. And the answers are... So an acetic acid solution, being a weak acid, contains mostly acetic acid molecules and hardly any ions. Scientists, being people, like to control things. We can shift the direction of an equilibrium reaction either forward or backward by applying Le Chatelier's principle. Stop the video, review Le Chatelier's principle, the different types of stress placed on a reaction, and how the stress is relieved. When a stress is placed on a reaction, the reaction is no longer at equilibrium, so the reaction will shift in a direction that reestablishes equilibrium. Here's an example. Reactants A and B are in equilibrium with products C and D. The equilibrium constant for this reaction equals 5. If reactant A is added, which is the stress, what happens to this ratio? The answer is the ratio decreases so it's less than 5. This tells us the reaction is no longer at equilibrium. To reestablish equilibrium, the ratio has to increase back to 5. The way to do that is to increase the numerator, which means more products forms, which means the reaction shifts toward the product side. So adding more reactant shifts the reaction to the product side and creates more products. Let's apply Le Chatelier's principle to see how we can get more salt to dissolve in water. First, let's write a chemical equation that represents salt dissolving in water. Stop the video and write that equation. And the answer is, since this reaction is endothermic, heat is considered a reactant. Stop the video again and apply Le Chatelier's principle to these three stresses. And the answers are, raising the temperature means we're adding heat, a reactant, which shifts the reaction toward the product side, so more salt dissolves. Salt and water are also reactants, so adding more salt and water shifts the reaction toward the product side and more salt dissolves. This reaction is used to make aspirin. Note that this reaction is exothermic. The reaction conditions to make aspirin affect how fast the reaction occurs and the yield of aspirin. Stop the video and review how these reaction conditions affect the yield of aspirin and answer the questions on reaction rate. And the answers are, using excess reactant or adding more reactant shifts the reaction toward the product side, increases the yield of aspirin, and makes the reaction go faster. But this reaction is exothermic, which means heat is a product. So raising the reaction temperature or adding heat makes the reaction go faster, but shifts the reaction toward the reactant side and lowers the amount of aspirin produced. A catalyst is not involved in the overall reaction, so it doesn't have an effect on equilibrium or yield, but makes the reaction go faster. In lab, we made a smelly ester by reacting an acid and an alcohol. We're going to go back to lab and figure out the reaction conditions to optimize the yield of ester. Here are the questions we want to ask and answer to determine the reaction conditions to make a high yield of ester. Let's apply Le Chatelier's principle to determine the reaction conditions to make Drano work better. Stop the video and answer these questions. And the answers are, for part D, this reaction is exothermic, so adding hot water is like adding heat, a product. That shifts the reaction toward the reactant side, which means Drano does not work as well. For part E, note that a gas is produced, so plugging the drain traps the gas, increases the pressure, and shifts the reaction toward the reactant side. So plugging the drain will not make Drano work better. These two reactions occur under the operating conditions of a car engine to produce NOx, which is a component of smog. It is NOx produced under high or low temperature or pressure conditions. Stop the video and review how Le Chatelier's principle helps us answer that question. So, if we do not want NOx to form, we should use low temperature and low pressure conditions. With more people, we need more food, and fertilizer is very important in growing food. 500 million tons of nitrogen fertilizer is produced each year. The industrial method to produce ammonia for fertilizer is the Haber process. Here is the chemical reaction. And here are the reaction conditions. Stop the video to answer this question. And the answers are: when pressure is distressed, the stress is relieved by shifting to the side with fewer moles of gas. Since this reaction is exothermic, a higher temperature shifts the reaction toward the reactant side and lowers the yield. So a catalyst is used to increase the reaction rate so a low temperature can be used. And finally, the ammonia product is removed during the reaction to shift the reaction toward the product side and increase the yield. Earlier in this course, we looked at how we can lower the freezing point of a liquid by adding a solute. Stop the video and take a look at this equilibrium reason for salt melting ice. Earlier in this video, we talked about equilibrium constant telling us the relative amounts of reactants and products. The methane combustion reaction has this equilibrium constant. Stop the video and answer these questions. And the answers are: since the equilibrium constant is huge, we assume that all the reactants will react to form products. We did this chemical calculation in Chem 1A. We looked at the Haber process to make ammonia for fertilizer a few minutes ago. The equilibrium constant for this reaction is very small. It's very hard to break that nitrogen-nitrogen triple bond in N2. The equilibrium constant tells us the relative amounts of reactants and products. Let's use the numerical value of K to calculate the amounts of reactants and products at equilibrium. Here are the data. We don't know how much nitrogen reacts, so let's call it X. Based on the coefficients in the balanced chemical equation, this is how much H2 reacts, and this is how much ammonia forms. Here are the amounts of each reactant and product at equilibrium. Let's plug these into our equilibrium constant expression and then solve for X. Solving for X is not easy since it involves solving for something beyond a quadratic equation. When we look at acid-base equilibrium reactions, we'll make a simplifying assumption which will make these types of equations easier to solve. For an equilibrium reaction, we can use the equilibrium constant to do a chemical calculation to calculate the amounts of reactants and products at equilibrium. So let's practice. Stop the video and set up an equilibrium calculation to calculate the amounts of reactants and products at equilibrium. And the answers are: I was able to solve this quadratic equation. Stop the video and figure out what value of X is the answer. And the answer is, if X equals 1.42, then the equilibrium concentration of H2 and I2 is negative. Stop the video again and determine whether these equilibrium concentrations match what the equilibrium constant is telling us. The answer is yes, there should be more products than reactants. We will get to practice more of these equilibrium calculations when we look at acid-base equilibrium reactions.